In this video, we're going to learn how to solve second-order non-homogeneous differential equations using variation of parameters. We'll start by looking at the equations that you can solve using this method and go over the formulas that you'll need to find the solution. We'll then walk through 4 steps that you can follow and work through an example so that you can see exactly how the method works. Let's get started. The method of variation of parameters is most commonly used to solve second-order non-homogeneous equations that look like this. ay double prime plus by prime plus cy is equal to g of x. G of x is called the non-homogeneous term, or it can be called the forcing function or the input function, and it can be any function. It is not restricted to be a particular type of function like it is when you're using the method of undetermined coefficients. The solution to this equation is y of x, and it's written as 2 parts. It's written as y sub c of x, or that could be y sub h of x. That is the complementary solution or the homogeneous solution, plus y sub p of x, which is the particular solution. The complementary solution y sub c of x is c1 y1 of x plus c2 y2 of x, and this is the solution to the homogeneous equation ay double prime plus by prime plus cy is equal to 0. The particular solution is written as u1 of x y1 of x plus u2 of x y2 of x. Here, u1 and u2 are functions that depend on x, and they vary. That's why this method is called variation of parameters. Y sub p is a particular solution to the non-homogeneous equation. Let's now go over how to find this particular solution. What you're going to do is you're going to substitute y sub p, that's right up here, into the non-homogeneous equation. You're then going to require that u1 prime y1 plus u2 prime y2 is equal to 0. That's just a condition that we can impose to find a specific solution to the non-homogeneous equation. I'm not going to go over the derivation, but when you make this substitution and impose this condition, you end up with these 2 equations. A is the coefficient that multiplies y double prime. Let's look up here on the right. It's right there. The assumption is that A is not equal to 0, which is basically saying we're assuming that we have a second-order equation. Now that we have these 2 equations, what we want to do is we want to find u1 of x and u2 of x. Our 2 equations have u1 prime and u2 prime in them. So we're going to solve for those first, and then we'll integrate and find u1 and u2. I think the nicest way to write these solutions are if we use matrix notation and we get the solution for u1 prime and u2 prime. If you're not familiar with matrix notation like this, don't worry. We're going to go over an example and I'll show you exactly how it works. The denominator for u1 prime and u2 prime is the same, and it's called the Wronskian, and you may have seen that before. Let's now go over the 4 steps that you can follow to solve a second-order non-homogeneous equation that looks like this. The first step is to find y sub c. To do that, you're just going to solve the homogeneous equation. Step 2 is to make an assumption that y sub p is u1 y1 plus u2 y2, and u1 and u2 are functions of x. Step 3 is to find u1 and u2 using these formulas that I've written down right here. We have a formula for u1 prime and u2 prime, and then you can find u1 and u2 by integrating. The last step is to just pull everything together and write the final solution as y is equal to yc plus yp. Let's now walk through an example where we're going to solve the second-order non-homogeneous equation y double prime plus y is equal to tangent x using variation of parameters. Our first step in solving this problem is to find our homogeneous solution, and we're going to get that by solving the homogeneous equation. So the homogeneous equation is just the equation that is on the left-hand side, and the right-hand side is equal to 0. So we have y double prime plus y is equal to 0. To solve this, we are going to let y equal e to the mx. This gives us m squared, that comes from two derivatives, e to the mx plus e to the mx is equal to 0. We can factor out an e to the mx, so we just have m squared plus 1 e to the mx is equal to 0. An exponential can never equal 0, so we end up with m squared plus 1 is equal to 0, and we can solve that for m. M is going to be plus or minus the square root of minus 1, so it is plus or minus I. Before we go further, let me write down the formula that we're going to need for finding the solution. If we have a root m equal to alpha plus or minus I beta, then our solution y sub c is e to the alpha x times c1 cosine beta x plus c2 sine beta x. We got that m is plus or minus I, so that means alpha is equal to 0 and beta is equal to 1. I'm looking right up here. Now let's write down our solution. Our y sub c is e to the 0 times x, so that's just 1. And then we have c1 cosine beta x. Beta is 1, so that's just cosine x, plus c2 sine x. And I guess we really don't even need those parentheses. So I'm going to go ahead and erase them. And there's our homogeneous solution. For our next step, we need to make an assumption about our particular solution. We're going to assume that y sub p is a function u1x times y1. So let's go back up here to our homogeneous solution, and let's let y1 be cosine x, and let's let y2 be sine x. So down in step 2, we have u1 of x times cosine x plus u2 of x times sine x. And I'm going to highlight that because we are going to need that later. In step 3, we are going to find u1 and u2. Remember, here's u1 and there's u2. Instead of going through the derivation and imposing the standard condition that you have to impose, I think it's easier to just look at these formulas and find u1 and u2. Let's first look at the formula for u1 prime. u1 prime is the matrix 0, and then g of x. G of x is our right-hand side. So let's go back up to our original equation, and let's do some highlighting. G of x is tangent x, and then notice that there is a 1 multiplying y double prime. So let's make a note that a is equal to 1. Tangent x is g of x, so we have tangent x here. And then a is 1, so we just have tangent x. And then we have y2 up here on the right. There's our y2. It is sine x, so this is sine x. And then derivative of sine x is cosine x. And then in our denominator, we have y1, which looking back up here to the right, that is cosine x. And the derivative of cosine is minus sine x. And then we have y2, which is sine x, and y2 prime, which is cosine x. Let's go ahead and let's find what this equals, and we'll worry about U2 prime in a minute. We're going to evaluate the top matrix. To evaluate a 2 by 2 matrix, you multiply the main diagonal elements and then subtract off the off-diagonal elements. So we have 0 times cosine x minus sine x times tangent x. And then we do that same thing for the denominator. We have cosine times cosine. So this is cosine squared x. And then we have a minus sine squared x. This gives us minus sine x tangent x. And notice our denominator is cosine squared x plus sine squared x, and that's a trig identity, and it is equal to 1. So our denominator we can just not worry about because it's equal to 1. Let me mark here that that was u1 prime. Now we're going to integrate and find u1. So it is the integral of minus sine x tangent x dx. To evaluate this, we need to rewrite tangent as sine over cosine. So this is minus the integral sine x times sine x over cosine x dx. Now we're going to go back up to our trig identity and we're going to solve for sine squared x. So sine squared x is equal to 1 minus cosine squared x. It's nice that we already had that. This becomes minus the integral sine squared, which is now 1 minus cosine squared x, all over cosine x dx. We can split this up. 1 over cosine is secant x. And then cosine squared over cosine is cosine. So we have minus cosine x dx. And that gives us the answer minus the integral of secant, which is the natural log absolute value secant x plus tangent x, minus a negative, so we have a plus the integral of cosine, which is sine x. And for now, we are going to add on an arbitrary constant, and I'm going to call this plus C3, because up top here, we already had a C1 and C2. I'm going to show you in just a few minutes that we actually didn't even need to write down that constant, but I think it'll be better if we go through the process and you can see why we didn't actually have to write that down. Let's go ahead and let's highlight this. And I'm going to mark down here that it is equal to U1. And we'll need that in a minute. Now let's go back up and we're going to find U2. U2 is actually easier. We start out with U2 prime. It is Y1, which is our cosine, and then Y1 prime below that, which is minus sine x. And then upper right is a 0, and then our g of x, that was our tangent x. And our a was 1. And then here's the nice thing. These denominators are the same thing, which is great because we already know that the denominator is equal to 1. So we don't even have to do anything else. Now we can compute U2 prime. It's the main diagonal elements multiplied, so that's cosine x times tangent x, minus the off diagonal elements multiplied, but there's a 0 there, so we just subtract 0. Let's now rewrite tangent, because we know that tangent is sine over cosine, so that cosine is going to cancel, and that's really great. We end up then with U2 prime is sine x. So U2 is just the integral of sine x. Much easier than U1. And we end up with minus cosine x, and I'm going to add on a C4. Now we have one more step, and we just have to put everything together. In step 4, we are going to write our final solution, as our complementary or homogeneous solution plus our particular solution. Y is going to be YC plus Y sub P. Let's write down what YC was. We found that YC was C1 cosine X plus C2 sine X. And now let's write down Y sub P. Y sub P was U1 of X cosine X plus U2 of X times sine X. Now let's go ahead and substitute in U1 and U2. From our last page, we found that U1 was minus natural log absolute value secant X plus tangent X. And then we had a plus sine X plus C3. And this gets multiplied by cosine X. And then let's add on U2. That was minus cosine X plus C4 times sine X. Let's go ahead and let's multiply everything out here because some things are going to cancel, which is going to be really nice. We have minus natural log secant X plus tangent X times cosine X plus sine X cosine X plus C3 cosine X, and then we have minus cosine X sine X plus C4 sine X. Notice that this term is going to cancel with that term. And now let's look at these terms. We have C3 cosine X plus C4 sine X. If we look back up to the complementary solution right up here, C1 cosine plus C2 sine, you can see that this solution and this solution are just duplicates of those solutions. So they're not adding anything extra. Because of that, we can just let C3 be equal to 0 and C4 be equal to 0. And that's always going to happen. So from now on, when you do one of these problems and you're integrating, you don't have to add on the constant of integration. Now let's put this all together. We are going to combine this equation and this equation. This gives us that our solution y is C1 cosine X plus C2 sine X minus natural log absolute value secant X plus tangent X times cosine X. And there's our final solution. And that's it. You now know how to use the method of variation of parameters to solve second-order non-homogeneous differential equations. You should now be all set to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.